Oh, I forgot to name it. Okay, guys, so welcome to the last chapter of this book. And this section is called Continuous Functions. And before I start talking to continuous functions, let me just tell you that it's a very interesting topic because we all have the notion of continuity built into our subconscious. So we kind of intuitively understand what continuity means. For instance, if you are stuck in a closed room and you want to go from this place to this place, you cannot just disappear from the square and appear over there. You have to have some sort of a trace, and this trace is continuous. Similarly, if, for instance, I don't know, it's raining where you are, and it's not raining somewhere else, then as you go from this place to this place, then slowly it will be raining less and less and less and less until you get to this place where it's dry. Or for instance, if you are driving, say, I don't know, from Tampa to uh, Arlanda, and I don't know how many miles it is. Let's say this is a 60 miles, so you start out at 60 miles away from Tampa and away from Orlando. And then at some stage, if you want to go to Orlando, you know that you will be 30 miles away from Orlando and 10 miles away from Orlando. In other words, your way is going to be continuous. So most of the things in nature that we observe seem to be continuous. And incidentally, when you go to nuclear physics and in particular to quantum mechanics, then it's actually interesting that it's not a continuous movement. So, for instance, if you have an electron moving around a proton, then it can move on this direction or it can move on a higher orbit, but it cannot be anywhere between those two orbits. So, when you go to quantum physics, then the things cease to be continuous. Okay. So, what is the notion of continuity? And to be honest with you, uh, mathematicians were looking for appropriate definition of continuity for many, many years. And right now, we settle on one particular notion of continuity, but it may not be necessarily the best one, but this is accepted in mathematical community. So, for instance, if I have a function that look like this, you will probably all agree with me that this function is not continuous. And if you have a function that look like this, you will all agree with me that this function is continuous. So a perfectly good description of continuous function is a function whose graph you can draw without taking the pen off the paper. For instance, if I have to draw this graph, I will draw this part, then I have to take my pen off and draw this part. This function I can draw without taking a pen away from the paper. So this is a very, very nice idea of continuity. Unfortunately, it's not very mathematical, and so far, in my opinion, we cannot find a good, perfectly good definition of continuity. So I'll give you what we have. I will return to this concept of continuity later on at the very end of my section, my of this chapter. But for now, I'll just deal with the proper definition of continuity. Okay, so before we define the continuity, we have to define another notion, and this notion is uh, you have you probably know it from calculus 1 that the limit of f of x as x tends to p is equal to q if for every epsilon greater than 0 there exists a delta such that if f of x, if x minus this delta depends on epsilon, and it also has to be strictly positive, and if x minus p is less than delta, then f of x minus q is less than epsilon. Now, there is another trick to this notion of continuity, which is to this notion of limit of a function, which is very unpleasant. And this is that not only x minus p should be less than delta, but it should be greater than 0. In other words, x has to take any value close to p except p itself. Now, the reason we need that is because, for instance, if I have a functions that look like this, and then whatever, and then it takes a different value, and then it continues to look like this. So let's suppose that this is 1, then the limit, so and this point is 1, 2. Then the limit of this function f of x, as x tends to 1, is equal to 1, although if x is equal to 1, then f of x is not equal to 1. Okay, so for this reason, we have this very, very unpleasant restriction that x minus p not only should be less than delta, but also greater than 0. Okay, so now let me rephrase this particular notion of continuity that you should be familiar with in a more metric space kind of way, because what it says is that the limit of f of x, so now f is a function from a metric space x into a metric space y, and the limit of f of x as x approaches p is equal to q if, well, if what? If for every epsilon greater than 0, there exists a delta, which depends on epsilon, and greater than 0, such that if the distance from x to p is less than epsilon, but greater than 0, strictly greater than 0. In other words, once again, I'm not allowing x to be equal to p, then the distance from f of x to q must be less than epsilon. Okay, so this is a definition that it's the same definition, only it is stated in terms of metric spaces, and now I will restate it in terms of metric spaces. So let's see, what does this mean over here, that the distance from f of x to q is less than epsilon? It means that f of x must belong to the neighborhood of q of radius epsilon. Do you agree with me? And this part of a definition means that x must belong to the neighborhood of p of radius epsilon. And the only other things that we have to require here is that x is not equal to p. Okay, so now we can do an appropriate definition in terms of metric spaces, that limit of f of x as x approaches p is equal to q. Now f here is a function from a metric space x into the metric space y. Of course, p is an element of x, and q is an element of y. And so this limit of f of x is equal to q if for every neighborhood of p, okay, this is my neighborhood of p, there exists a neighborhood of q such that if x is not equal to p, no, it's another way around. Sorry, for every neighborhood of q, there exists a neighborhood of p such that if x is not equal to p and x is in this neighborhood of p, this implies that f of x is in the neighborhood of q. Okay. So these are just equivalent definitions that I'm giving you. One of them is expressed in terms of absolute values. The other one is expressed in terms of neighborhoods in the metric space, but these are all the same definitions. And well, let's see. I hope you can see all of them, right? Okay, so these are the definitions. The next part that I want to talk about is the relation to the convergence of functions and convergence of sequences. And there is a relation, And so here's the theorem. And people in analysis like this theorem very much. So a theorem, and the theorem says that f is a function from a metric space x into the metric space y. Again, p is a point in x, and q is a point in y. And the limit of f of x as x converges to p is equal to q if and only if. So this is if and only if. If and only if what happens? If and only if for every sequence xn, so now xn is a sequence in x, such that xn converges to p, we have this sequence f of xn. So this is now a sequence in y. So this sequence converges to q. Okay, so if you look at this theorem, what I'm doing here is I'm reformulating the convergence of functions in terms of convergence of sequences. There are two reasons why we like it. One of them is in analysis, people far prefer to deal with sequences than with limits of the function. But the second reason is that we already proved a bunch of theorems about sequences. So instead of proving them about limits of the functions, we're going to use this theorem and convince ourselves that uh, this particular equivalence allows us to very, very easily prove a bunch of theorem without working. And since mathematicians are very lazy, we like it very much. So let's work on a proof of this theorem. And the proof of this theorem, so the first part, I'm going to assume that the limit of f of x, yeah, incidentally. So in this case, xn converges to p, but xn is not equal to p for infinitely many. Remember, I have to have it in such a way that xn converges to p, but xn is not equal to p in a sense. And of course, in terms of sequences, it means that there are infinitely many xn's which are not equal to p. In fact, you can assume that xn's are just not equal to p to begin with, and that's enough. So I'm taking all possible sequences such that they're not equal to p, but they converge to p, and then I require that f of xn converges to q. Okay, so now I'm going to assume that the limit of f of x as x tends to p is equal to q, right? And I'm going to take a sequence xn not equal to p such that xn converges to p. Now, what does it mean that xn converges to p? It means that for every epsilon greater than 0, there exists an n, such that if little n is greater than capital N, then the distance from xn to p is less than epsilon, right? That's the definition of a convergence in this case. But what I hope you don't mind is that if I change epsilon to any other letter, it would still be the same thing. It would say that, for instance, oh, I don't know, for every delta greater than 0, there exists an n such that if n is greater than capital N, this implies that the distance from xn to p is less than delta. So I hope you agree with me that this is exactly the same thing. I just change uh, epsilon to delta. Okay, so let's continue with the proof. So let's suppose that I have a sequence xn which converges to p. Xn is not equal to p. And I'm going to assume that this limit of f of x as x converges to p is equal to q. So what does it mean? It means that for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance from x to p is less than delta and greater than 0, then the distance from f of x to q is less than epsilon. Do you agree with me? So in particular, if I'm going to choose n so large that the distance from xn to p is less than delta, that would imply that the distance from f of xn to q is less than epsilon. In other words, it would say that this means that xn converges to p, but this means that, look what we got. We got for every epsilon greater than 0, there exists an n greater than 0, such that if n is greater than capital N, then the distance from f of xn to q is less than epsilon. And so this means that the sequence, remember, this is a sequence. This is like f of x1, f of x2, etc., f of xn, etc. Then this sequence converges to q, and we proved one half of the theorem. So now let's prove, okay, so I hope you can see. Now let's prove the second half of this theorem. So this time I'm going to assume that for every sequence xn such that xn tends to p and xn is not equal to p, we have f of xn converges to q. Okay, and what do I want to prove out of these conditions? I want to conclude out of here is that limit of f of x as x converges to p is equal to q. Okay, so the proof is by contradiction. Suppose not. And now I want you to think about it for a second. So what do we have to prove? We have to prove, let me use a different color here. We have to prove that for every epsilon greater than 0, there exists a delta greater than 0 such that if the distance from x to p is less than delta and greater than 0, then the distance from f of x to q is less than epsilon. Okay, now I want you to think about it for a moment and realize what would be a contradiction to this particular statement. Well, what would contradict this statement is that it's not true. So not for every epsilon there exists a delta. In other words, there exists an epsilon strictly positive. Let's say epsilon equal to 0.0001, whatever, such that no matter how I choose delta, for any delta greater than 0, uh, this is not true. In other words, there exists an x such that x is not equal to p, the distance from x to p is less than this arbitrary delta, but not equal to 0. And yet, the distance from f of x to q is strictly greater or equal than epsilon, which is this fixed number being 0.0001. Okay. Are we good so far? Okay, so this is what we're assuming. And so now I'm going to pick this epsilon. Remember, I'm proving it by contradiction. I'm assuming that something like this is true, and I'm going to pick an epsilon greater than 0. Again, let's suppose that epsilon is equal to 0.0001. Okay, and this is what it says. It says that there exists an x such that this is true and this is not. So in particular, if I choose my delta to be equal to 1 over n, this implies that there exists an xn such that 0 is less than the distance from xn to p, which is less than 1 over n. Okay, and yet the distance from xn to q is strictly greater than this number epsilon. Okay, so what does this inequality means to you? This inequality means that xn converges to p and xn is not equal to p. And this inequality means that the distance from oh, this is distance from f of xn. So, and the distance from f of xn to q is strictly greater or equal than epsilon. In other words, the sequence f of xn as a sequence, this is a sequence, it does not converge to q, and we have a contradiction that proves the theorem. Okay, so this is a very nice theorem, as I said, for two reasons. Why? One, people in analysis like it very much, but the second reason is that now we can use everything we know about sequences to prove results about the limits of the function. Okay, so let's try to do that. I mean, here is the theorem or corollary if you want. One, that if limit of f of x as x approaches p equals to q, and the limit of f of x as x approaches p equal to q1, then of course q is equal to q1. In other words, I'm stating here that the limit of the function is unique. Well, let's prove it. The limit of f of x as x approaches q equals to p, it means that for every sequence, in particular for some sequence xn, that converge to p and not equal to p, we have this sequence f of xn converges to q. Now, if this was also true, then the same sequence f of xn would converge to q1, and we know that the same sequence cannot converge to two different limits, so this implies that q is equal to q1, and we're done. Okay, so it's a nice proof that uses the property of convergent sequence to conclude something about limits of the function. Here's a few more, and this time I'm going to take only functions f and g, and this will be functions from metric space X, but inter R or C. The reason I need that is because now I want to add and multiply those functions. If this function is some other metric space Y, I wouldn't know how to do it. All right, so let's do that. Now I form another function f of x equals to f of x plus g of x. So this is a new function from x into my field being R or C. And what I claim is that the limit of f of x as x approaches p exists. And not only that, but it's equal to the limit of little f of x as x approaches p plus the limit of little g of x as x approaches p. So if you think of this limit as being, say, q, and this limit as being q prime, then what you conclude is that the limit of f of x plus g of x plus g of x as x approaches p is equal to q plus q prime. Okay, so let's prove it real quick. So what do we have to prove? I'm going to take a sequence, arbitrary sequence, xn, such that xn is not equal to p, and xn converges to p. And then I know that this sequence f of xn converges to q, and I know that the sequence g of xn converges to q prime, and we know that the sum of two convergent sequences converge and converges to the right thing. In other words, f of xn plus g of xn for sequences must converge to q plus q prime, and my conclusion is that for every sequence xn not equal to p, the limit of f of xn plus g of xn is equal to q plus q prime, and therefore the limit of f of x plus g of x as x approaches p is equal to q plus q prime, which is equal to the limit of f of x plus the limit of g of x. Now notice that in this case, x must approach the same point p in the bottom. Okay, so in a very identical fashion, we can prove that once again, if f of x and g of x are two functions from x into R or C, well, in that case, if limit of f of x is equal to q, x approaches p, and limit of g of x, x approaches p, is equal to q prime, in that case, the limit of the product of that function, f of x times g of x, as x approaches p, is equal to q times q prime, which is equal to limit of f of x times limit of g of x as x approaches p. Okay. Again, let's prove it real easy, just using nothing else but sequences. So I know that if xn is arbitrary sequence that converges to p, and xn is not equal to p, that implies, well, that implies two things. That implies that the limit of this sequence, f of xn, remember this is a sequence, is equal to q, and the limit of g of xn, again, this is a sequence, is equal to q prime, and we know that the product of convergent sequences converges and converges to the right thing. In other words, the limit of the product of these two sequences, fxn times gxn, converges to, is equal to q times q prime. Now, this over here is nothing else but the function f times g evaluated at xn, and that converges to q times q prime. And so, therefore, I conclude that the limit of f times g of this function of x as x approaches p is equal to the limit of f of x as x approaches p times the limit of g of x as x approaches p, and that proves the result. Now, what else do we know about sequences? We know that the ratio of the sequences converges provided that the limit of the second sequence is not equal to 0. So the conclusion here is that if I have limit of f of x, once again, as x approaches p is equal to q, limit of g of x as x approaches p equals to q prime, and if q prime is not equal to 0, okay, let's try it again. If q prime is not equal to 0, in that case, the limit of f of x over g of x as x approaches p is equal to q over q prime. Again, how would the proof go? Well, very easy. I'm going to take a sequence xn not equal to p such that xn converges to p. It means that f of xn converges to q, g of xn converges to q prime. These are two convergent sequences, and q prime is not equal to 0. So my conclusion is that this sequence, f of xn divided by g of xn, converges to q over q prime. And once again, by the previous theorem, we get the conclusion that we want. Okay, so one more quick remark here about this particular section, that if my functions f and g happen to be from a metric space X into Rk, so instead of R, I'm now taking the Rk. Well, I can still add the functions, and still the proof is exactly the same, that the limit of the sum of the two functions is equal to the sum of the limits. I cannot multiply the functions, but I can take the dot product of the function. So what I want to say is that the limit of a new function, so this is a dot product of f of x times g of x, and this is a my notation. The Rudin likes to use f of x, and this is a bar, times g of x, which is a bar, meaning that these are vectors, and this is a dot product of these two vectors, that this is equal to nothing else but the dot product of the limit of f of x as x approaches p, here x approaches p, times the limit of g of x as x approaches p. And once again, the proof is completely trivial. It just goes along the same way. Take a sequence xn that converges to p and not equal to p. Then we know that f of xn converges to q. G of xn, it's a sequence which converges to q prime. And that means that the dot product of these two sequences, f of xn, g of xn, by the theorem from the previous chapter, converges to, converges to the dot product of q and q prime. And what that means is that because this converges for every sequence, it means that f of x times g of x, so the dot product is now a new function that maps x into R, and the limit of this new function, f of x, g of x, as x approaches p, is equal to the limit of f of x as x approaches p. Now, this is a vector, and this is a vector. And now I'm taking the dot product of these two vectors, and that's the end of the story. Okay, so now I'm going to stop this particular video and then return with the second part of this video. And